I am Pedro dal Castel. I am a student, PhD student at Indiana University under James supervision. And our quick notices here, every session is being recorded, transmitted, and distributed. Um, Also, we have links to the slide deck. It's on the chat. We can send it again. Hayden can send it again if you need. And again, thanks to our supporting institutions, IUB, Biocomplexity Institute, OpenVT, Glimprint, NIH, and NSF. Okay, so today's topic is diffusion. And I will start by not talking about diffusion. I will give you a slide on the links of previous years' workshop and class materials in case you need something with more details about about the content that we are lecturing, because this year's workshop is a little bit summarized. And if you want like more details, more workbook style, you can access these links. These are previous year's materials. And I'm still not talking about diffusion because yesterday we saw how to use cell dictionaries to store information. And this is the actual syntax in a more organized way of what you should be doing. So in the start function, you can initialize an attribute of a cell by using the syntax cell.dict and then open close square brackets and then under quotes the name of the attribute. So this is a dictionary, which means the entry is a string, and then you can attach any kind of value, object, function, anything to this dictionary entry. So for example, you can attach a string. For example, it can be the state of a cell. Let's say the cell is in state um, apoptotic. Then you can write apoptotic and attach that to one of the dictionary entries of the cell. It can be a value, a scalar, a float, an int, anything like that, an imaginary number, whatever. For example, if you want to save the position of the cell in the previous step, you can use dictionaries to do that. You can also save a history. So let's say your cell remembers the values, the past values of something for some memory mechanism, whatever. You can attach a list of numbers instead. You can also get the syntax using the code snippets into edit. So if you go to the CC3D Python drop-down menu, go to cell attributes, you can access and modify dictionary attributes. Then also remember that if your cell divides, if you create a new cell, then you have to instantiate a dictionary to that new cell too. Okay? If you try to, for example, access dictionary entry of a cell you created but did not instantiate the dictionary with that entry name, you will find a bug. If you want to share information between classes, you cannot do it directly. So if I define a variable, a self variable inside a class or a local variable inside a class, and I have more classes in my steppables, I cannot simply refer to them in another class. But one way of doing it, of sharing variables between classes, is by using the shared steppable vars dictionary. And then this dictionary you can use on multiple classes and pass information between classes. So today's module learning objectives and topics are understand the basic idea of diffusion. And as exercises, we are going to generate linear and exponential scalar fields in CompuCell3D. Our topics are fields, representation of fields, concentration, gradient diffusion, time scale of diffusion, diffusion in biology, effect of the environment in diffusion, diffusion equation, boundary conditions, diffusion solvers, and interpretation of diffusion. Why are we studying this? Because diffusion is one of the main ways signals are transmitted in tissues. And why do we need signals? Because cells communicate by, for example, secreting substances. The substances propagate in space, often via diffusion, and these signals are received by other cells. So the critical things we're going to learn here is how the signals are created, transmitted, and received, uh, how it's transmitted by diffusion, um, how fast the signals propagate, how intense they are at the receiving cell, how far they travel into the region. And we will build two simulations that explore the concept of diffusive fields as means of signaling. The first one is a very basic ecosystem where one bacteria consumes nutrients, generate waste that another bacteria consumes, and the avascular tumor spheroid where the tumor cells consume a nutrient field and they grow and divide based on the concentration of this field. And when cells are deprived of nutrient, if they are too distant from the nutrient sources, then they die and we can get equilibration of the tumor. So let's start with what are fields. Is my volume okay? Like,
They're fine.
okay. So fields are basically measurable physical quantities associated to each point of space and time. So they can vary in time and in each point of space in the region you are exploring, there is an associated value. For example, scalar fields. Each point in space has an associated scalar value. So the title is incomplete. It has to be a scalar value, for example, a real number. Energy is one example of scalar field. So you can have energy or energy density in space, concentration of a substance, temperature, charge, density of a molecule, density of cells, viscosity, height. And in this example here, the temperature of the oceans being represented by isolines and heat maps. The scalar fields are represented by heat maps, isolines, surfaces, uh, and in 3D, for example, where it's very hard to see the fields, we usually use isosurfaces. And isolines in maps, this is very common, where the line represents a constant field intensity. We also have the vector fields. They represent vectors. So in each point of space, there is an associated vector, which is both a scalar that represents the intensity of this vector, the absolute value of this vector, and the direction where this vector is pointing to. These can represent, for example, fluid flow, fiber orientation, cell polarity. And let's jump to some questions here. So give me an example in the chat of an important scalar field to biology, an important vector field to biology, and also another type of field that is not scalar or vectorial, also with a biological application. Okay, cell polarity. But that's a bit too easy, right? Because I gave cell polarity as an example here, so let's be creative. Oxygen concentration, Rodrigo for scalar field, okay? Rodrigo. Concentration, cytokine concentration, chemical gradient. Okay, interesting. Chemical gradient is an example of a vector field. Migration direction is a good one. Vector field. Electric field is a vector. Growth factor. Okay. What about a field that is not scalar or vectorial with biological application? Position. No. Position is not a field. Stress tensor. Fantastic. Yeah. Stress tensor. So I have the answer on the slide. So stress and strain tensors are good examples of fields that are not vectorial or scalar. They are tensorial fields, and they have biological application as far as I know. So here are the answers. But we will focus on concentration fields because diffusion happens to concentration fields. Other fields like vectorial fields, they will obey different laws. For example, the Navier-Stokes equation or similar. So examples of concentration fields in biology, you can have cytokines, nutrients, hormones. Those are the main ones. But you can also talk about concentration of viruses, concentration of bacteria, so on and so forth. They are often represented by intensity, by heat maps. For example, a heat map is basically what you see when you have fluorescence, for example. The fluorescence tracks the concentration of a chemical, but you can also represent as a curve. So we're using C as a variable for the concentration field. So for the as the notation for our concentration field that has a value in each point in space and also varies in time. So this is our surface representation of a field. The field here is in 2D, and then the third dimension, dimension Z, represents the field intensity. Then we have the gradient of a field. So gradient and intensity are different concepts, and people often mix them, but gradient is a vector field generated from a scalar field. So imagine you have a concentration field like in these shape here. Then the vector field is in each point of space, there is an associated vector that points uphill. And the intensity of this vector, the absolute value of this vector, is the slope of the curve. So the scalar field is represented by this shape, and the vector field is represented by these arrows here on the xy plane. So these vectors are pointing uphill, and the intensity of these vectors, the length or the absolute value of these vectors, is the slope of the curve in the point where you're measuring the gradients. The general definition is the derivative of the field with respect with each coordinate of space in the direction of each coordinate of space. So derivative of f with respect to x in the direction of x plus the others. And then again, let's not confuse intensity with gradient. So the gradient is the derivative of the intensity, the spatial derivative. They are not the same thing. Stress and strain do not have well, I'll let moderators answer that. Let's do an exercise now. So here I have a one-dimensional field um, given by this curve. So this is our profile. In the axis, I have position, and in the y-axis, I have the intensity of the field. So in points A, B, C, and D, what are the gradients? There are three options here. I'm giving you three options. First, the gradient has positive absolute value and points to the left. The gradient has positive value, absolute value, and points to the right. So I'm talking about positive value here. So absolute value. Or the gradient is zero. So there are three options, and you associate one of these options to each of these 4 points. Y-axis is the intensity of the field, and the x-axis is position. A point A, 0, point B, positive to the right, C is 0, D is negative. Okay. 1 is D, okay. 2 is B, okay. And then 3 is A and C. Perfect. Okay. I think you guys understood the idea. So I will show the answers. B, again, gradient is the slope and it goes up a hill. So B points to the right and D points to the left. C and A are on extremes, on maximum and minimum, where the slope is zero. So the gradient there is zero on both. Okay? All right, now let's talk about diffusion. Diffusion is the transport of material, passive transport of material from high to low concentration regions. And I will list a bunch of stuff to make sure you understand what is required and not required for diffusion to take place. You don't need work. I mean work by energy. Um, you don't need someone or something uh, inputting energy on these molecules so that they spread. Diffusion is passive, does not require work done over the system. It does not require a medium to take place. So you don't need water, you don't need air. It can take place anywhere. It does not require interaction between the involved particles. The particles do not need to collide between each other to happen. It is spontaneous. It is irreversible. Okay. It assumes some thermal fluctuation. It needs some agitation, some kinetic energy to randomly move these particles around. It takes place in space and time, so it requires space and time. And Fick's law is a model of diffusion, the model we are going to use, which states that the flow of matter is proportional to the difference in concentration between the two regions. And you can see diffusion. So in this video here, you're seeing two regions, one starting with a high density of particles. And by mere probability of exchanging particles, the region with more particles will lose more particles than the region with less particles. And the steady state is achieved when both regions have the same number of particles. And in this beautiful example by 3Blue1Brown, which I recommend if you want to learn more about partial differential equations and the diffusion equation, which is the same as the heat transfer equation. Not the same in all aspects, but in the first glance, it's very, very similar. You can see how things flatten out, things smooth out. This is diffusion taking place. If you start with a sharp Gaussian, as time goes on, this is as the distribution of your field, the profile of your field. As time goes on, these Gaussian will flatten, and the total area under this Gaussian is conserved because you are not losing or gaining material in the system. There is this other example here where the molecules or the particles start clumped together, and simply because they have different velocity orientations, they don't need to interact. Just because they have certain different velocity orientations, they bounce around and spread out. In biology, diffusion is cheap transport of molecules. So oxygen distributes itself on tissues, and there is no need for a specific cell or a specific molecule to transport oxygen around. Of course, in the blood that happens, but the blood is because it's a long distance travel. Over short distances, diffusion drives diffusion of most molecules. It takes part in signaling processes like inflammation, hormone signaling, distribution of nutrients. I just mentioned oxygen, but toxins, lipids, etc. can diffuse through the tissue. Cells control how diffusion takes place by employing barriers like the cell membrane. Also inside the cell, you have other barriers. You have the mitochondria membrane. They are selective for certain molecules and let other types of molecules go through. They also employ channels to selectively allow molecules to diffuse through the membrane. And all of these barriers, the cell density, ECM, fibers, all of that, even cell receptors can affect how those chemicals diffuse through the tissue. Because these, for example, these molecules can bind to fibers in the ECM, can bind to receptors in the cell, on the cell surface. And cells can also absorb these molecules and not let them escape the cell. So all of these mechanisms will affect how diffusion takes place. Even though there are many different um, um, issues regarding diffusion, like molecules getting trapped, etc., we model all of them using diffusion. And diffusion, we need an object, which is a scalar field. The behavior of this field is diffusion. It can interact with other objects in the system, for example, secreted by cells or taken up by cells or being degraded by something. Uh, they have boundary conditions. We have to specify how these fields interact with the boundaries. We can specify, for example, periodic boundary conditions, which we have seen in the previous lectures. No flux, constant value, constant derivative, constant flux, and you can basically create any boundary conditions in CompuCell3D in the Python code. And for the dynamics, the diffusion equation, which is our next step. So the mathematical model of diffusion equation expressed as a partial differential equation. This is a video of one field getting solved computationally. Again, if you want more details on how these partial differential equations work, how they behave, how they are solved, go to 3D Blue and Brown. It's the best. So the main behavior here is that peaks and valleys flatten with time, and the speed which diffusion happens is proportional to the diffusion coefficient d, which is multiplying this Laplacian here. And also the sharper these peaks and valleys, the faster they flatten. So you can see that it starts much faster, these smoothing out, and then as it gets smoother and smoother, diffusion is lower and slower. We have many boundary conditions to choose from. Periodic, so assume you have an initial state like this, a droplet, and then periodic boundary conditions allow the field to cross boundary and reappear on the other side. There is a GIF here of the asteroids game where things cross the boundaries and reappear on the other. This is what's happening when you choose a periodic boundary condition. Constant derivative, and here I'm giving an example. Most used example, constant derivative equals 0, which means that there is no material being exchanged at the boundary. So in this case, we have a conservation of the total field integral, same as in the periodic situation. And when you hold the field at a constant value in this last case, then the field has to obey this constraint of having a certain value at the border, and it will behave such in a way that the field value is 0 here on the borders. However, you can set to other values. You can set a constant value equal 1, equal 10. You can even set negative numbers, although for concentration of molecules, negative numbers don't make much sense. Diffusion is often spatially heterogeneous. What does that mean? For different uh, places in the region, you can have different diffusion coefficients. For example, a diffusant may diffuse faster in water than in fat, than in a cell, than in ECM. And in CompuCell, you can set different diffusion coefficients depending on the cell type, for example. This is possible, and we'll see later when we implement diffusion on our simulations in the XML, you have a section here where it says diffusion coefficient cell type, and then you can modify the diffusion coefficient for the specific cell type. Same thing you can do with decay coefficient. You can set decay coefficient specific to cell type, as well as secretion rate, uptake rate. When the diffusion coefficient is heterogeneous, the diffusion equation looks a bit different. It is and I just forgot the name of the first operator. It is so it's the divergence of the diffusion times the gradient of the concentration field. And why do we have to do this? Because diffusion now depends on the position. So diffusion is a field itself, a field, depends on the coordinates of the system and concentration as well. So we have to account for that. However, in CompuCell3D, we still use the good old diffusion coefficient, diffusion equation, assuming that the diffusion is homogeneous in space. So this is formally this is incorrect. However, inside cells and inside medium, the diffusion is still homogeneous. So this discrepancy will only happen at the border of the cells, which does not introduce critical issues. When you search for diffusion, especially on YouTube, they often show this example of a dye droplet diffusing in a cup of water. This is incorrect because when you drop the dye in the cup of water, there is advection, there is fluid flow, and that's what's driving the mixing of the dye in water. So there is this very cool video that showing that if you put dye very carefully in water, we're making sure that the water is sitting still and the density of the dye is very similar to the density of water, then it looks as if the dye is frozen in time, which is very cool. Basically, proving that diffusion is extremely slow. It's much slower than you think. So for our scale, our human scale of like centimeters and meters, or feet and inches if you're American, um, it's not something you can perceive. It's not something you can observe, but it is effective at short distances of micrometers and tens of micrometers, like inside a cell, between cells. So I have so the relationship of time and distance here is quadratic. The time it takes for a molecule to go a given distance is proportional to the square root of the distance. So the longer the distance, the more time it takes. For example, if it takes 1 second for a molecule to displace 1 micrometer on average, if you want this molecule to displace 2 micrometers, you wait 4 times the time. I have an estimate here, 5 minutes for oxygen to penetrate on average 10 cells deep into a tissue. And 100 cells will take 9 hours. So this is just to give like an idea of how slow diffusion is and why it is mostly relevant at short distances. So here we have the definition of diffusion time, which is more formally what this concept is. Uh, so the diffusion time is proportional to the distance squared, this average traveling distance of our molecule, divided by d, where d is the diffusion constant. I have caveats and like a more formal explanation of the diffusion time. I won't go into the details because here we just need this intuitive understanding that the time, diffusion time goes with the square of the distance. But if you really want to be formal and understand what is the exact relationship here, why does it make sense, and how it relates to the dimension of the system, then you can read this whole slide here. We'll have now an exercise on boundary conditions. This is about like thinking boundary conditions. So I'm first going to revisit the boundary conditions to make sure um, nobody forgot already what they are. So given an initial state of a droplet, the periodic boundary conditions will allow the field to cross the boundary and reappear on the opposite. The constant derivative sets the derivative of the field, the rate of change of the field at the border. If you set that to 0, it means that basically the boundaries are walls. They are not allowing exchange of the field with the outer medium. And constant value 0 holds the field at value 0 on the borders. It could be other value, it could be constant value equals 10 or something else. What I imagine when I'm thinking about a constant value equals 0 is a reservoir. So imagine you are like, um, there is like an incense here, or like a candle, something that emits something that diffuses in my room. If I open the door or if I open the window, where there is another system out there which is much bigger than mine, I will consider that a reservoir with 0 concentration of the field. So for this situation, I would consider that the boundary condition for this chemical that I am secreting here, that I'm producing here inside my room, has boundary condition 0 at the window if I open the window. Constant derivative 0, I understand as the wall. So the wall is not allowing chemicals to escape or get in. And periodic boundary condition, I understand as an infinite space. So if there are many people out there with their candles on, I would use periodic boundary conditions for that purpose. Now let's apply this to an example. So this exercise, I'm asking you, what is the appropriate boundary conditions for each of these cases, 1 to 6? I will go through the cases one by one, and you will choose the appropriate boundary conditions for each of them. So in the first case, we have epithelium and the atmosphere above the epithelium. Okay? And with respect to a cytokine field. So there is a cytokine field in this epithelium and the atmosphere above. How does this field interact with this boundary of the epithelium with the atmosphere? Second case, to the sides, there is just more epithelium doing the same stuff as the site you're looking at. So what will be the appropriate boundary conditions for this boundary? Third case, there is another tissue type below the epithelium behaving as a reservoir. You could imagine that there is like I forgot the name of the tissue, but some other tissue or like blood vessels taking these cytokines away, or the lymphatic system, whatever. Okay. Fourth case, you have a gland producing a hormone, and you are just modeling the gland. And then one of the boundaries is a duct, like a vessel, something that is carrying something much bigger than the gland itself that is carrying these hormones away. Finally, I have fifth and sixth case. So I have a tumor and a blood vessel. So I'm not modeling the blood vessel, but the system that is the tumor and the ECM, they make boundary with a blood vessel, which should be providing oxygen. And also to the sides, if you look at the sides where there is ECM outside the tumor, there should be more ECM if you keep going to the sides. So what would be the appropriate boundary condition for that? So 1 to 6. Let's go. Note that if you set constant value equals zero, you will have loss of your field to that boundary. If your field is positive, is a high value, and the boundary in question has a constant value of zero, you are losing the field to that boundary. So these are the answers. And I will go through the answers one by one, explaining why I'm choosing these types of boundary conditions. So epithelium with the atmosphere, there is no exchange. I mean, the tissue is not losing cytokines to the atmosphere, and the atmosphere is not providing cytokines to the tissue. That's why an appropriate boundary condition there is constant derivative equals zero. So there is no exchange of material. Epithelium, they look the same. It's as if the epithelium is going on forever. So we are using a periodic boundary condition on 2. For 3, there is another tissue working as a reservoir, which means that if the cytokine goes there, it gets lost. So you could use constant derivative 0 or constant derivative another value, depending. For example, these other tissue could have a baseline secretion rate of cytokine, and then you could set like constant value of some small number. Same idea for the gland. You can set a constant value 0, which means whatever the gland is producing is getting lost to this duct. Or you can, for example, from experiment, you get what is the average concentration of this hormone in this duct, and then you set some small value. But setting it to 0 would be a good first approximation. Now for the tumor, option 5 here, sorry, question 5, you have ECM, and there is just more ECM going on. So maybe you should set to periodic. However, if you set that to periodic, it's as if you have another tumor here on the right, another tumor here on the left. So that's debatable. Maybe there could be other appropriate boundary conditions, like constant value, maybe, where you set the profiles, the measured profiles. Yeah, periodic might not be the best one here. So this is debatable. And for 6, well, we have the blood vessel. Let me see what people answer to this one. 6 is not periodic. For sure is not periodic. 6 constant value. 6 is not constant derivative. So why is it not constant derivative? First, because it is allowing exchange of the oxygen. The blood vessel is providing oxygen, but it's not pumping oxygen. If there is a higher concentration of oxygen outside the blood vessel will receive oxygen. It's not periodic because periodic would be assuming that there is like just more ECM down here. But that's not true. There is a blood vessel. So the right thing to do here is let's assume the blood vessel replenishes the oxygen concentration fast enough that we can say, okay, constant derivative equals a certain value. Sorry, constant, yeah. The boundary condition is a constant value equals a certain value, which is the concentration of oxygen in blood. All right. In CompuCell, there is a question here. I will see whether the moderators can answer or defer to me if it's something more that everybody should know. In CompuCell3D, we have various diffusion solvers that you can choose, and they have their situations. For example, the steady state diffusion solver, it's not actually solving the diffusion equation. It is solving the Laplace equation, which is this one on the right. So the Laplace equation is the Laplacian equals 0, which you derivate from the diffusion equation assuming steady state. A steady state, again, is the time derivative of the concentration equals 0. If you want more details on that, also on all the possible diffusion solvers you can pick, You can go to the documentation on our official website and you see everything there. Why do we choose steady state diffusion solver sometimes? Because if the diffusion coefficient is extremely high, and it will be very expensive to simulate all the way to the steady state. So instead of solving the transient of the diffusion equation, you solve directly for the steady state. If you care about the transient, which most of us do, we use a diffusion solver FE. This is the standard diffusion solver. Generally, this is the one we pick. And will be the one we are focusing on during today. Finally, the reaction diffusion solver FE allows you to specify multiple fields that interact with each other. You can specify multiple fields on the other ones, but the reaction diffusion solver allows those fields to interact with each other. For example, field A destroys field B, or field B creates field C, so on and so forth. So on and so forth, yeah. So let's start by importing the diffusion solver into our CompuCell3D simulation via Wizard. This is specific for version 4.6. If you are on version 4.7, then the window will be a little bit different. And what I suggest you do is create the field such that it shows up on the table, but don't bother with specifying parameters. Just create a field and then hit next. So the create the simulation normally one cell type, all like no like only like default settings. And when you arrive to the chemical fields page, you write the name of the field just like if you're adding another cell type. You do that for the field. You type the name of the field, select diffusion over FE, hit add, and then the field shows up in the table. And then you can hit next, and then you hit next, 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 and that's all we need. So these are the instructions. I will go over these instructions with you side by side. Very straightforward. Give it a name, select diffusion solver, and click add. Again, here, you should give it an acceptable name. You cannot use spaces, you cannot start with a number, and you cannot use special characters. Ritesh asks, isn't 1 and 3 the same? No. So 1 atmosphere, something infinite working as a reservoir? No, because cytokines do not diffuse to the atmosphere. But great question. So here I'm going to create a new simulation. Normally, as you guys always did, new CC3D project. Then from here, you give it a name, Python plus XML, next, next. Here you can set a cell type, doesn't really matter. Next. So now here on the chemical fields, we give it a name like oxygen. By default, diffusion solver FE selected, and then I hit add. And then the chemical field shows up here in the table. And then you can hit next, 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 and finish. Don't worry about the cell properties and behaviors. And repeat the steps here. I'll cancel this. CC3D project, new CC3D project. Then next, next. I give it a cell type. Next. Then oxygen for the field name. Diffusion solver FE add. There we go. Correct. That's correct, Derek. You don't need to choose anything in the cell properties and behaviors. Now next, so after setting the chemical field there, you don't need to worry about cell properties and behaviors. You can just go next and finish. So here I open the simulation on Reddit, and if I run this, what do I have? I have this because I didn't set any behaviors for the cells, which is okay. And here we can visualize our field. So if I pause the simulation and come here on my graphics window, there is this drop-down menu with the cell field selected. I can select the visualization of the field like oxygen, and this is my field over here. Okay? It's not behaving as I want, and we'll see why. There is another way to import Diffusion Solver to your simulation. In case you already have a simulation running, working, everything, and you don't want to reinstantiate another simulation, create another simulation from scratch, what you can do is use the to edit code snippets. So in this menu up here, CC3D you go to Steppables, and then click Diffusions over FE. Make sure you are on the XML and select an empty space of the XML outside other syntax blocks. And then you select your diffusion solver. It will insert a diffusion steppables to your simulation. Now we will set up the coefficients, boundary conditions, and the initial field profile. So first step here is to find the diffusion solver steppables in your code. So I'm going back to my XML. This will be here on the XML. Then I scroll down and I find steppable diffusion solver FE. So make sure you find that on your XML diffusion solver FE. And here you have your diffusion field name. You have the global diffusion constant. You have the global decay constant. And then you have the diffusion coefficient by cell type. So you can make cell types have a different diffusion coefficient than medium. You can also set a specific decay coefficient. Here, it's coming with these secretion lines. So you can also specify secretion via XML. And the boundary conditions down here, which come with certain values, certain configurations. In my case, it's coming with constant value and constant on X and constant derivative on Y. We're going to change that. So make sure you find this chunk of code. And now what we want to do is set all the decays to 0. So find the steppable diffusion solver and then global decay constant, you set that to 0. But there is also a decay coefficient for the cell type. Set that to 0 as well. So 0 on the global decay and also 0 on the cell type. Decay, not diffusion. Diffusion 0.1, keep it at 0.1, and decay coefficient you set to 0. Were we supposed to create a cell type? No. No. It doesn't matter. I created the cell type, but it doesn't matter for this exercise. Just make sure the checkpoint, the thing you have to make sure here is that you have diffusion solver FE steppable on your XML. If you have that, you are fine. Were we meant to do so? No, you were not meant to do so. Were you meant to create a cell? No. Choosing no properties, that's correct. 4.7, what do you best put for the boundary condition setup page after the solver? We'll go through the boundary conditions in a second. But you don't need to set them in the wizard. You can wait for the exercise. We are going to change it on the code. Diffusion constant 0.1 here, 0.1 global, 0.1 cell, and then 0 decay. Do we have diffusion inside the cell? Yes, we have diffusion inside the cell. Let's move forward. So inside the diffusion solver, there is a secretion part. And at least in my version here, it's coming with secretion 0.1 for the cell. Set that to 0. Set secretion to 0. Simple. Just modify the secretion value here to 0. What do we do if you don't have the line? Just don't do anything. It's correct. If you don't have the line, it's fine. Good question. Because we changed a bunch of these stuff for the 4.7 version. And here for the moderators, here the goal is to create eventually the linear gradient. So if you want to skip ahead and just do that, it's okay. What actually happens when secretion is set to 0 biologically? Well, if you set secretion to 0 in the model, the cells don't secrete anything. Like in a human being, if you set secretion to 0, it dies. Yes, I will show you how to observe the field. So look here. In the graphics window, there is this drop-down menu. Uh, it's usually selecting cell field like this. And then you change to oxygen, and it's the blue here. This is how you see the oxygen field. Okay, moving on. Next step here, set boundary conditions to periodic. So I'm coming back here to my boundary conditions, and I will comment out. This will probably need a bit more space. So here I will select these two lines that I don't want, and then I'm pressing Ctrl/ to comment. And then I uncomment periodic by clicking the line and pressing Ctrl/. I will do that one more time in case you didn't see what I do. So I am using the command Ctrl/. I think it's command/ if you're on Mac, to comment out the lines that I don't want and uncomment the periodic line because that's what we want. You can also manually comment and uncomment, but this is easier. So just click the line there, Ctrl/ to comment, and then uncomment periodic, comment, uncomment periodic. Is secretion in CompuCell3D equal to a reaction term? Yeah, kinda. This is just like changing the boundary conditions for now. Are you sure it's Ctrl/? Is there another way? Yes, there is another way, which is coming here, edit, and then block comment, uncomment. Edit, block, comment, uncomment. There is this command here. Okay. If you don't see periodic, write it. That's my suggestion. You comment out whatever is there, and then periodic. If you already did that, then you can set an initial concentration profile. Here I am setting a single droplet point with intensity 100 at position 20, x equals 20, and y equals 20. So this goes here on initial concentration expression. You can uncomment that line, and then here you type that down 100 times, and then x20, y20. So at the x equals 20, y equals 20 position, there will be 100 field intensity. And that's it. If you've done this, you can run your simulation and see what happens. Silvani, it's okay. Yes. The different versions will show different things. All you need is to set that to periodic. If you have this to periodic and the other things commented out, it's fine. It doesn't need to look exactly the same. Johanna got it correct. Perfect. So I'll launch the poll here, see if you guys reached this place here. So again, here I'm setting periodic boundary conditions and the initial concentration expression up here, 100 times x20, y20. Don't forget the double equal. A single equal does not work. What are you supposed to observe in the player? If you did all of this, you are supposed to see one dot spreading. One red dot spreading. So Maria is seeing how the field spreads, and because of the periodic boundary conditions, the field appears on the opposite boundaries. Perfect. So let me run my simulation here and see what happens. So here, okay, I have my field here. It's a single point and then it spreads and it fades. However, we want to adjust these settings so that I can see this the field profile. So to do that, I will show you yeah, so as a homework you can try different boundary conditions and different diffusion coefficient, but what I want to jump to is configuring the field visualization for 2D and 3D cases. So to configure your field visualization, you go to Tools, Configuration, Field, and then here you can set a minimum and a maximum for your field. So yeah, this should, oh yeah, now, okay, there we go. Now it's, you can see that the color bar here is rescaling to minimum, sorry, to the minimum is 0 and the maximum is whatever is the maximum of the field. And as it spreads, because of the boundary condition, I can see that the field starts to appear on the opposite borders here. So I see that some people got it correct. Just let me pause here and come back to the configurations window and go through some of the options. So you can select your field to which you apply these settings. And the settings are fixing or unfixing the minimum and maximum. So if I fix the maximum to 100, what happens is that the point quickly fades because it's scaled to 100. Let me step this. So you can see the null point here, and as I am stepping, it quickly fades because my color bar here is fixed. If I unfix this, then the color bar will automatically scale according to the field maximum. So I keep seeing these droplets spreading as time goes on. You can show contours, isolines, which is more for the 3D cases. We're not going to use this much during this lecture, but there is this option here. Ekaterina, if you're not seeing any points spreading, uh, likely you didn't set your initial condition expression. You can also, yeah, at least for the next exercises, you can download a working demo code. So if you are struggling to follow the steps, you can just download the code from the student materials, and that code hopefully runs with the answers. Because of time, I will move to the next exercise. So as a homework, you can try different diffusion coefficient, different boundary conditions. You can also introduce cells and set a different diffusion coefficient on these cells. Now let's set up a linear field. So to set up in a linear field, what you want to do is set constant value on the x min and x max borders. So for example, 1 on the left and 0 on the right. And then the initial state doesn't really matter because any initial state you set, the diffusion equation will eventually reach a steady state where it's a linear field, constant gradient from left to right. So as long as you're doing constant value 1 on the left and constant value 0 on the right, or something like that, you will get a linear gradient. Remember again that field intensity and gradient are not the same thing. But to make sure we reach the steady state or we are at the steady state already, what we want to do is to draw a linear field from start as our initial concentration. To do that, we can write any expression, and the expression for a line that starts at 1 and ends at 0 for a lattice, the lattice that we chose. Here, my lattice is 256, so I will do 1 over 256, but you can do 1 over 100 if your lattice is 100 by 100 pixels. But the idea is the same. So here, 1 over this times x plus 1. If I don't change my boundary conditions, I just I just get something that is like slowly equilibrating from the sides. You can see that I have a linear gradient here, but it's slowly spreading. This is not what I want. What I want is that the linear field is static. So I will change my boundary conditions to constant, sorry, leave periodic on the y-axis, yeah. And then just on the x-axis, you change the to constant value 1 on the left, which is min, and 0 on the right. And if you do that, then your linear field will be static, like so. So this is the exercise. I will pause this, show the code to you guys so you can see what's going on. So try to get the linear gradient. And I'll give you a couple of minutes to build a linear gradient before going to the exponential gradient. For this specific exercise, you can download the demo code. I'll go through the steps again. So here, first you set an initial concentration expression of a um, uh, line, linear, profile here. So I'm setting -1 over 256 because 256 is the size of my lattice times x plus 1. So this means that my field on the left is 1 and it's 0 on the other side. Perfect. People are getting great results. Even though Johanna looks disgusting. I mean, your simulation, not you. I'm sure you look great. This is great result because this shows that you know how to set initial concentration profile, you know how to set boundary conditions. I think what you're missing there, Johanna, is constant value boundary conditions on X. So your X mean is 1. Probably your X mean there is like 0. So X min 1 and X max is 0. So that it goes from high on the left to low on the right. Yeah, people are getting great results. Mika, I think you have periodic boundary conditions on your X. So change that to constant value, and then show me your initial concentration profile, Johanna. Clara, if you have white vertical lines inside the field, those are the ISO lines you set. Taylor has the wrong initial concentration profile, but that's okay. Van has the wrong initial concentration profile, but that's okay too. If you just increase a lot your, by the way, if you're not getting the proper initial concentration expression, if you just increase your global diffusion constant to like 10, it's just a matter of time until you get the appropriate linear gradient. But I think the results are great, even though some are wrong. They are still great. They show that you guys understood more or less what to do. Again, initial concentration expression, this line here on the slide is -1 over 100. This is assuming you set a 100 by 100 lattice. Here in my case, my lattice is 256 by 256. So my initial concentration expression is -1 over 256 times x plus 1. Boundary conditions, constant value on x, 1 to 0, and periodic on y. Again, you can change field visualization here. You can fix min and max. This is for the color bar. I already explained this. And finally, the exponential field profile. So if you keep your simulation as it is and set a global decay constant to something like 0.001, then you should get these profile here, this exponential profile, where you have like more blue on the right and less red on the left, something more steep than the gradient, the constant gradient, which is very flat, very homogeneous. So to generate this exponential field, all you need to do is set a global decay constant, something like 0.001, 0001. This is enough to generate this exponential field. You can keep the initial concentration expression the same. Just make sure you have the proper boundary conditions. If you don't have the proper boundary conditions, things will not look great. And if you don't have the proper initial concentration expression, this is not a problem. You can just set a very high diffusion constant, something like 10. And why don't I do that right now? So set a very high diffusion constant there so that you see that the field changes much quicker and then you achieve your steady state profile quicker. Oh, it was constant derivative instead of constant value, and I didn't see that. Oh, it was constant derivative. Look at that. Okay, yeah, that's a problem. What do you mean by insight, Mark? I will go over why that's the case in a bit, but this is all we need to do for this exercise for generating the exponential field profile. So I will run this and oh, look at that. I have a different decay coefficient inside the cells. That's why it's different. The field profile is different inside the cells and outside, which is very cool. If I come back to my code and let me set like a higher global decay, and I will also set that to my cell to make sure it is happening everywhere. Now I run this, and you can see how I'm getting less red and more blue. It's getting these exponential shape. So if you're seeing this, your field collapsing to an exponential profile, this is fine. Then, very good. Yeah, you have a different decay for your cells than medium, but that's good. You can also download the demo. So this is done and it's uploaded on the drive folder, student materials, demo, demos, day 3, and then you see the exercise there. All right, so I'll move on. Decay constant and coefficient are names I use interchangeably. So it's okay to call it both. If you're having trouble, you can talk to a moderator, or you can also just download the demo and run. So what is decay doing? Decay is basically a loss of the field intensity proportional to the local intensity of the field. So this we see in radioactivity, for example, as the more radioactive material you have, the more it decays, and the less we have, the less it decays, but it's always decaying, and we have this loss of material in time. We also see that in breakdown of molecules. For example, oxygen depletes inside tissues because it is consumed by cells. When you have decay in the diffusion equation, there is a relaxation time. So there is a typical time it takes for your field to reach the steady state. And this is 1 over the decay coefficient. It is the time it takes for the field to reach 37% the initial value. Okay? The decay equation is simply the rate of change of your field is proportional to the intensity and it's negative. And the rate of change is given by the diffusion constant. In the diffusion equation, decay just enters as a negative term here. So you have your normal diffusion equation, then minus gamma c. Gamma is the decay constant, c is the intensity. Decay happens everywhere in this equation, and the steady state depends on the boundary conditions. So for example, if you have periodic boundary conditions and no secretion, no sources, the steady state is 0. And if you set like a positive constant value, then your steady state is something different than 0. So it depends on the boundary conditions. But here, the overall behavior is that you are losing intensity on time. As for your intuition about decay, the higher gamma, the faster you lose field, and the lower the decay, the slower you lose field. This is very useful and will be very useful to building our demos, our simulations, our models today. Because, for example, in tumors, tumors absorb nutrients, and there is a typical distance that this nutrient field can reach into the tumor. This is what we call diffusion length. The diffusion length is like reach of the field into a region where decay is taking place. Diffusion length is given by the square root of the diffusion divided by the decay coefficient. And applications of that are, for example, distance between capillaries because cells are taking up nutrients, and then every so often you need another capillary to make sure cells are receiving enough nutrients. And the further you are from a capillary, less nutrients you have because every layer of cells is consuming a little bit of nutrients. You can derive this relation by assuming steady state and solving the diffusion equation, assuming an exponential profile of the field. Just a quick reminder, you can set diffusion coefficient and decay coefficient per cell type. And again, CompuCell3D, although you can set heterogeneous diffusion coefficient in space, CompuCell3D still solves the diffusion equation by using the um, simple diffusion equation, which is technically incorrect, but it doesn't introduce great big artifacts because inside cells and inside mediums, the diffusion is homogeneous. So I have a few slides on the intuition of the diffusion constant. And the basic intuition is that the higher the diffusion constant, the faster materials spread. But there is also the geometrical interpretation, which is that the width of this field profile grows with the square root of time or the variance of this distribution. This is a Gaussian, by the way. The variance of this distribution grows with time. And finally, there is a particle interpretation where you have all these collisions between particles and then things diffuse around. These all refer to the same idea of diffusion. Now, in the next lecture, we are going to cover how to implement sources and uptake on cells. So what is a source? Source is basically adding material to the field. This we implement in CompuCell with secretion. So if you want a cell to be a source of material, you let the cell secrete material. For example, a tumor cell could be secreting VEGF that promotes vascularization, for example. And this enters in the diffusion equation by simply a positive term. It does not depend on the intensity of the field like decay does. It's simply a constant pumping of material to the field. The different applications here are secretion, excretion, and synthesis. And we also can implement sinks. Sinks is the same idea as a source, but it's negative and it's removing material. Here we have to be careful that if we set a negative secretion to a cell, our field can get negative. So there is another way we do it, which is uptake instead of negative secretion, which I will cover on the next lecture. If you set both secretion and decay on your system, then your system equilibrates in a value that is given by S over gamma. S again is the rate of secretion or your source rate, and gamma is your decay coefficient. Because you are always secreting at a constant rate, and gamma depends on the concentration of the field, so they will always equilibrate at some point. For example, in a muscle releases lactic acid, but also degrades lactic acid, or uh, maybe blood is taking lactic acid away at a rate that is proportional to the concentration of lactic acid. And on the long term, the concentration of lactic acid in muscle stabilizes. So the steady state is given by S over gamma. So in CompuCell3D, and you can try that by yourself. You can freeze your cells, and then set a secretion rate for your cells and a decay. And if you do that, you see that your field inside this region will equilibrate to a certain constant value, while we can still diffuse to other regions. The tendency is that inside the region where you have both source and decay, is that it keeps around these S over gamma value. And again, because we have decay, we have an equilibration time given by 1 over gamma. So this is the typical time it takes for the system to equilibrate. So as a homework exercise, you can create a group of cells, set decay and secretion coefficient in these cells, and observe that the ratio between the two determines the value at steady state. So if you set secretion 0.1 and gamma 0.1, your steady state value concentration is 1, because it's the ratio that matters, is not the absolute values of both. So you can set, for example, 10-10, and if you set 10-10, the steady state is still the same, but because your gamma parameter is higher, your decay is higher, it equilibrates faster. These we use to model secretion, excretion, and exocytosis, which are different concepts. Secretion is when a cell produces a signal, something that is not going to something that will be used by cells, or yeah, are useful. Excretion is something that is waste. It is related to waste, something that the cells are not going to use anymore. Exocytosis is a process, um, is one mechanism of secretion, but you can have other kinds of secretion other than exocytosis. So there are other means of secretion that are not exocytosis. I don't remember the names exactly, but there are other means. It doesn't need to be vesicles and um uh, docking, etc. If you want to read more about this, you can go to Wikipedia. We don't need details on the biology. We are modeling all of them the same way, which is source. Then, for specifying secretion in CompuCell3D, you can define the rate, and there are two kinds of rates, let's say. You can set a cell to secrete a chemical by applying a constant rate. So it's basically what we saw. It's a constant rate, a positive number you add to the diffusion equation. So every Monte Carlo step, the cell increments a field by a given amount of material. If you set to constant value, it's the same as the boundary condition. It's the same as the constant value in the boundary condition. The cell, instead of pumping material to the medium, it will hold the field as at a constant value. So imagine a cell that is secreting something, but when it's sensing that the field concentration is at the optimal value, it stops secreting. This is an appropriate situation to use constant value. Uh, you can also specify where secretion occurs. You can set secretion to occur at the boundary of the cell, at all internal pixels of the cell, and also at the center of mass of the cell. So I have different snapshots here exemplifying. So the first one, all pixels of the cells are pumping material into the field. The second case, just the center of mass. So there is a single pixel secreting. Again, notice that when you have more pixels secreting, you are secreting more field. So if you change from all pixels to center of mass and the other way around, you have to adjust the secretion rate. Generally, generally what I do when I use always all internal pixels and I divide the amount secreted by the volume of the cell. You can let only the borders of the cell secrete. And you can also choose if you want to secrete on the outer pixels outside the cell or in the inner pixels inside the cell. So these are two snapshots here. These fourth case, the cell is secreting inside. And I just froze the cell and set the diffusion 0 on medium pixels. And here's the other way around. I froze the cell. I set diffusion 0 inside the cell and secreting on the outer pixels. Lastly, you can also set conditional secretion. For example, let's say your cells just secrete a material when they are in contact with another cell of a given type. This is what I'm showing these two snapshots here. So here I'm setting conditional secretion of the cells in contact with medium. So you can see that only at the borders with medium, the material is being created. And this cell, exactly this cell here in the middle, this cell is not secreting anything because it has no contact with medium. And of course, you can implement secretion in the Python code and you can set any condition you want. You can say, oh, only the cells that are on state X can secrete. Only cells with a certain volume, only cells, no. You can create any condition imaginable. So we covered the basics of source, secretion, equilibration time, the steady state value when we have secretion and decay, the specification settings for secretion in CompuCell3D, and in the next lecture we will focus on model building exercises. Let me go over the discussions here. Can be heterogeneous in the boundary of the cell, similar for uptake, but not in a polarized way. You can absolutely set one pixel to secrete a value different from another pixel. You can do that. It's quite painful to do it this way, but yes, you can. Uh, how do you synchronize the Monte Carlo step with, okay, this is a question for Michael. Michael got it. But should we define secretion either at the XML or at the stepable's Python file? You can do both. In the next exercise, sorry, in the next lecture, we'll go over how to do it. And we will focus on on setting secretion on the Python file because it's much more flexible than the XML. So for example, in the model that I am building for my research, I I do everything on Python because I have to run my simulation on a cluster. And if I have XML on a cluster, we'll do everything on Python. Also because sometimes you want to condition your secretion rate to a certain scenario. Let's say if a cell senses a certain chemical, or if a cell is in contact with a certain, like more than two cells, for example, then I secrete a chemical. This is much more easy to write on the pure Python section rather than on the XML.
All right, thank you, Pedro. Please do take a minute to fill out the modular experience questionnaire.
If you face challenges during the exercise and you want to get the simulations running, working properly, we can enter a breakout room or we can chat here.